Hi. So I'll be talking about localization and mapping, and in short, we call that Islam. So we'll go through why we need it and in general how first humans do it, and then go from there. So usually traditional localization techniques like GPS, motion capture, these usually fail, and I'll demonstrate how. So one by one. So in case of GPS, what you can see in the video is that the drone is stationary, but the position of the drone is changing on the readings which I get on my end. And why is that? Because you have IMU drift, your GPS does not work at very high hertz and all those things. And even traditionally, if you don't have a very high grade GPS, again, your accuracy is also limited to 1 to 2 meters. And there will be loss of signal if you go underneath some tall buildings or trees, or even if you have metal sheets around you because of multipath reflection. And in general, it's very unreliable in dynamic cluttered environment, and we don't really want to rely on just the GPS. So then there are technologies like UWB, which uses again RF to localize yourself. So what you see in the video is that there are four RF beacons kept on the ground, and the drone has one, and then the drone is trying to localize is using that. The problem is that this infrastructure cost is so heavy. Its accuracy is good, everything is great, but infrastructure cost is just too vast, right? You have to put so many beacons if you want to just go from uh, one hall to the other hall. You have to cover all that whole place with a bunch of beacons. So it's high cost. Then again, you have to maintain those beacons. If one beacon goes down, then you have to replace it. So maintenance cost also goes quite high. Uh, Then the other kind of systems which we usually use to localize drones and other systems is motion capture, right? You have these LEDs, IR LEDs, IR beacons on top of your drone, and or you can have like a passive tracker, so be some balls kept, and then you have arrays of camera which try to see where the drone is, and then using the vision from all the cameras try to localize where it is in the relative volume of the But problem with this again, it's capital intensive. You have to put so many cameras across the hall. If you have to just go from one room to the other, you have to arrange full array of cameras in that, right, to localize the drone. So it's again impractical to use it in big terrains or large volumes. So let's go back a bit and see how humans do, because I, in general, think that humans are the best robots available. So, uh, humans usually would utilize something like a map, and the map would have these annotated locations like, oh, look at this bend in the path, or this lake is going to be somewhere here. And of course, you have latitude, longitudes all plotted on top of a map, and then shapes and other things help you. So you can think of it in a different way, like trying to generalize what we're trying to actually use when we try to localize ourselves using a particular map. What do we generally use? So I would say we're trying to utilize features. So map has certain features, and we're trying to find those features in real world and try to see, okay, where could I be, and we see where you are related to those features, and then in the map where those features, we can generalize where you are in the overall world. That's great. How do you make robots do it? So first we need sensors, right? So we need to equip the whole robot with multiple sensors, both proprioceptive and extroperceptive. So extroperceptive is looking outside. So a LiDAR camera, so you can see the LiDAR on the top. This is the LiDAR, and then this is a 3D camera. So you need these things to see how the world looks like. But you also need to know how the world is, how we are evolved. Right? So usually humans will have ears which help us localize how are tilted left, tilted right, and things like this. So IMU for robots is the equivalent to that, right? So using these sensors, you put into the brain, right, the compute board, and then you try to merge the uncertainty and all those things and try to get the best out of, or try to generalize where you are in the world and then see where you stand in the world as well. So let's go back to how we started the journey for localization for the robots, right? So where am I the robot for? Uh, the Randall Smith and the Peter Cheeseman's paper was where I would say the Slam journey got started, right? And as the paper says, it's that spatial uncertainty, right? So one thing I would like to point out is even if you have these expensive or really accurate cameras and lidars, you still will have a lot of uncertainty, a lot of noise, not just from the sensor, but also from the world. The world is not perfect, right? A bottle uh, which looks at me does not might not look as the same bottle for the other person. There will be dents in the bottle over a period of time, but you need it's still a bottle to a human being. Just drawing references, right? So the world is also inaccurate in a way. So how do we deal with it? Before we go and jump into the challenges and other things, let's figure out what we are trying to do. So SLAM is basically, or localization is basically the problem of where I am and how, like, where in both position as well as in the force, in the whole space which we have. And what are the kinds of inputs I'll get from it will be the control command. So how can I move for I move 10 steps, right? It's a control command which I give to my robot, sensors data, how I see from my eyes or from the cameras, and prior knowledge, the previous knowledge of the world, if I have, and if I don't, then that's a different case of it. But the localization problem is haunted by these four problems, right? One is this motion unpredictability. Even if if I tell you to go straight, the robot might not move straight. It might move 2 degrees towards left, but I asked it to move straight. So there's motion unpredictability in that. Since a measurement uncertainty, I might have asked to detect this world, this room which I'm sitting in, but there will be certain noises, so certain rays might not reflect back to me in a LiDAR, or the camera might not see something because there's a defect in the camera, or there might be a small flickering which happens, which whitewashes the whole camera frame. Like you're taking a photo and somebody puts a flashlight in front of you for half a second, you'll not be able to see it, right? So these are all like sensor uncertainties and measurement uncertainties which might happen. Compute constraint. You don't have infinite compute. Right? Even if today's world, even with i5 and i7, it's not infinite compute. And always remember, you need to remember this is that this localization is going to act as an input to a bunch of other systems. A bunch of other systems have to actually run alongside this. Can't hog all the computation available to you. So you have to be very particular about minimizing the compute map or the compute resources which you take from a particular processor. As well as same goes with memory. So that can be RAM as well as your normal hard disk or cold storage memory. Mapping errors. So this is what I would say is I saw the world the first day, Indian roads, right? You go on one day, next day, maybe for 10 days it might look the same, but 11th day the things might change a bit. There will be one more portal here, or there's a new building there, or there is a new store which opened up, right? These are new features. It's propped up in my map, but my map happened. No, all these are like my mapping errors in a way, right? So if you think about it, so I might not, if I go on the same road and I go, let's say, to that same town after 10 years, I might not be able to localize where I am in the town right away. It might take me some time. Human beings also take some time if the city has changed drastically. So, how do we model these uncertainties? So, one good way to do it is just think everything is probabilistic. You go to a gym, you see a rack, you see there's a probabilistic graph, right? So, this is usually how a gym rack would look like. It's 40, 45 is where the mean is, where most of the people put the rack in and lift the weights, but might not be the case for all the gyms and for all the weight machines. But yeah, so you start thinking in more probabilistic fashion. Now, how do I represent these things, right? So I will go over in the next coming slides how to represent these things. So for now, bear with me. The state X is just a combination of X and Y position and the theta, the heading position. 3D also is there, so you have roll, pitch, and yaw with X, Y, Z is also there now, but we'll mainly stick with the 2D world. Right? And what are we trying to understand also? Given a particular observation, eyes, or in the case of robots, so let's just talk now from the perspective of robots, given the camera's input or LiDAR input and a particular control, right? So I move further 10 meters or 12 meters left or whatever the control inputs. Given these two things, I need to condition my X state, or what is my X state, where I am, given that these are my initial commands and these are my initial observations. But one thing we are missing, right? Map. So how do we get that into the picture? So let's look at a bigger problem statement, right? So this is we're marginalizing the problem, right? Let's say we predicted the whole path from 1 to t, correct? And now we need the map, sure. But we do have all the observations and all the control inputs. In dx1, 2, 3, these are all like intermediate states I go through to reach to my point. So it's like asking this particular equation, I can put it in this way that given all the probabilities of taking all the paths, intermediate path at intermediate points, what is the probability of reaching this state? The state, what? What is that state? XT state. Also, get the map out. So 1 to t is all the observations, all the control inputs. What is the probability that I reach to this point? So what is the probability? Let's say you gave all your entrance test control. Its control will be giving your entrance test, and the observation will be seeing your results and seeing going through your counseling and stuff. What is the probability that I end up watching this video and learning about Islam? So think of this was all the paths which you could have taken. What is the probability you end up here at this point? Right? So it's a little bit philosophical. Uh, so few tools which we would use in future to reduce our equations and just make math a lot cleaner. Uh, I call this tool as conditional independence tool. Right? So we are assuming that xt state can is a complete. The state is complete in nature, so it in itself it can define all I need to know about where I am, the xt variable. And if that is the case, let's say, do if I have to predict this xt state, what does it depend upon? It depends upon how I move from my previous state and my previous state. Correct. Given that, okay, we don't have we're predicting, right, at this point, how I go to this next state. Do I really need to know how I moved back in the day? Or let's say if I come to a room, are you really thinking about how I woke up in the morning or how I came in the lift? No, not really. We just think about the last step and then you think about, okay, what's the next step I need to take to just reach to that position? So you only need the UT and the last state to predict this new state, right? So UT tells you how to evolve from the last state predictions, right? Another thing to note here is ZT, so observation. So given all my states, given all my previous observations and all my control inputs, what is the probability that I would see a particular observation? This is the imagining power. I close my eyes, I imagine if I'm moving back, I'm at certain place in the building, on the ground floor of the building. What do I do to move to the top floor? Right? How would the top floor look like? And that's what I'm trying to figure out here. You know, does it really depend upon how I moved, that how the world would look like? Assuming XT is a complete state, right? No, I just need to know where that XT state is, and that should just tell me what the world looks like. I don't need the control input. I don't need my past observation. So that's what this second equation represents. Now let's talk about this thing called as belief distribution using this video. So we'll use it a lot in this thing called as recursive Bayes filter. I'll introduce that as well. But let's look about belief distribution, right? So imagine you have this 1D world, right? And there's a robot there. Belief tells you, with how much belief do I know? Okay, so what is this thing called belief distribution? So this is basically used in this whole concept of recursive Bayes filter, right? In Bayes belief, what do I call it? All right, let's talk about this thing called as Bayes filter. So to go over this concept, we'll go to this really nice. All right, so next up, we'll talk about this topic called as Bayes filter, and also get to know these few tools, this tool called as belief, or the concept of belief and stuff. Uh, Imagine there's a 1D dimensional world in that there are these 9 states, which you could, 10 states which you could be in, and three of the states have like a door, right? So the 2 and 3 have a door here. And I have a robot, 1D robot, which thinks with a particular belief that where it could be, right? So the belief is all constant in our use case. Yeah, so you have this 1D world, and the robot exists in that 1D world and can move across these states, and you are trying to figure out for the robot where it is. And the only way you can understand where it is by seeing these doors. So it has the ability to sense if that particular state has a door or not. So belief PX basically tells you where you are in this whole state space. With what belief can I say that I'm at the state 5 or state 4 or at state 3, right? So let's see that. And another thing which we have the privilege information is observation data. Given a particular state, what is I get certain observation. So let's say I go to state 2, I see a door, and this is what my observation could look like. I could be at any of the door. I just saw one door, but am I at the door 2 or door 3 or door 7? I have no idea. And we can basically multiply that probability of px with the belief probability, right? So then now, okay, I know with certain belief I could be at door 2, door 3, door 7 because I saw only one door. Could be at any of these doors. Then let's say I next move 1. So this is my control input. I have this control input. I move 1, but there can be an uncertainty to it. So you can see that the graph of belief has spread a little. Standard deviation of each peak has increased more, right? The peak somewhat still says that I might be at the state 3 or a 4, depending upon whether I was at a 2 or 3, or it could be at 8 also if it was the 7th door which I detected. Now we again saw a door. Again, this comes and then we multiply with the previous belief. And no, wait, now I saw 2 doors. There's only one went back. I can say with good amount of certainty that I am at door 3, right? And that's great. Now this robot moves further as well, and then standard deviation the peak has dropped down a bit because there's a lot of motion uncertainty, and then it moves one more and it sees, oh wait, there is a gate at the end. So the observation peaks will come in, they'll get multiplied to the belief peak, and the belief will go higher for the state. So say with a higher certainty I'm at door 7 because I just went across these 4 positions and it saw the door again. So this is what a recursive Bayes filter looks like, and this is what I would, if I say in a more mathematical fashion, I can say it in this way. So I will first predict that I believe that I would be at this state, and that prediction is then enforced with an observation. So here, please note, so when I'm predicting the Bell prediction, right, I'm predicting that I might be at this XT state given my own past observations and the input control input which I got. But then I can correct it and then say that, oh, for sure, I for sure know that I am at this state after I get that particular observation. So this is how a belief distribution works in general. And these are just few more examples. I'll just let the videos play out and let you think for a minute of why the graphs would be moving in this particular way. Know that the graph again peak comes down a bit again because of the motion uncertainties and stuff like. And this is a very good example, right? So you have two doors together, right? So I'll let this play out. Saw the first door, prediction comes in, observation comes in, belief gets updated. I move forward, prediction happened, observation happened, correction happened, I move. So now you saw that my belief, let's go back again. I saw two doors back to back. Does it mean I'm at the second door now? Not really. I could have started from the door fifth and then moved to the seventh door as well. So I could be at the seventh door, I could be at the second door. But then when you see the sixth door again, it's like, oh no, so I was at one and two, and rather than being at the six and seven. So my belief went up higher. Then you see another observation, okay, becomes much better. We saw the two doors and then waited for a while in the States and then saw the two doors again. So that's how the map got really nicely updated. So yeah, now coming to the math side of things and how we can build this recursive filter. These are that belief and the belief, right? So if you think from Bayes' theorem, right? So what would be the probability of being in the XT state given my all observations? I use the Bayes' theorem to split all this out. This bottom term, because this is just observation and depends upon the past, and then that I can just probably negate this because it's like a scaling factor, right? This is not going to change depending on which state I am in, so I don't really care about. I'll put it as neta and call it a day. Now, you remember those conditional independence thing which you were talking about, right? See how this whole big equation, that observation equation, because it just depends on my current state which I'm in, simplifies it quite a bit. And same case with this, I this xt z1 minus c, that's actually the predicted belief, right? So I can, so this is how my new belief equation would look like. So I have the predicted belief, I get the new observation given that I am at that particular xt state, and then I update my belief. And we can go on and same case, so the xt, the conditional dependence part comes in, and I have this new state, smaller part, and then I can simplify this last part into just that. What was my last corrected belief? I'll take that, and that's how I'll add, okay, how do I go from the xt minus 1 to xt state, multiply that, and that's the probability or the predicted probability of being in the xt state. Because remember, I have to take into account what my previous belief looked like. So even in our animation, we saw that it took the belief, and if the spread kept happening, if it just kept moving without any new observation and without any new correction, thing used to just the standard deviation used to keep increasing, but the uncertainty keeps increasing till you get any correction step. Because you're just relying on this uncertain control input, right? So that's the consequence of this whole equation, which I wanted to enlighten you guys with. And then you can just put all these two things together, and that's how you can get. So in general, a recursive Bayes filter will look something like this. You have this previous prediction, previous corrected belief will be used for the next prediction step, and then this prediction will be used to build the use for the correction step, the present correction step, and then this correction step output would be used for the next predicted step, and then so on and so forth. And that's why the name recursive, right? So for this, yeah, incorporating the new measurements and stuff. So I think I went there. There's a prediction step, and this looks familiar, and then you correct yourself with a particular landmark and etc. I would say human beings also work with, right? So for this presentation, that would be all. Hope you guys join for the next lecture.